In the last slide, we talked about how we can improve NNet, the net population. Now we want to understand exactly how different factors affect NMR signal intensity, which is directly proportional to the macroscopic nuclear magnetic moment, M0. What is M0? It is a summation of all mu days in a sample. Because mu days are magnetic moment vectors that spin about the cone's axis of symmetry. Their x and y components are always cancelled by their opposite equivalent vectors. And hence, the summation of mu days is equal to the summation of their z component, mu j z. M0 being a macroscopic nuclear magnetic moment can be presented as a directional vector that lies on the sample's axis of symmetry and aligns with B0. Note that now we talk about the sample's axis of symmetry, which is different from the cone's axis of symmetry, which is why M0 is drawn on one side of the graph. Note that, strictly speaking, M0 should be subdivided or grouped by nuclear species, for example, M01H, M013C, etc. In other words, they can be grouped by the species gyromagnetic ratio, gamma. In fact, they are significantly varied with 3 cubes of gamma, not the square, as can be seen in the formula on the right, which tells us why detecting nuclei with higher gamma, such as 1H's, is always preferable. The expression also tells us that M0 is directly proportional to the square of B0, which is why high-field NMR spectrometers perform much better. It also tells us that M0 is inversely proportional to the square of temperature. However, dropping temperature is often not used in NMR experiments, because a low temperature can change the physical status of a sample, which can induce other problems. We will talk about this later. In brief, the expression tells us exactly how NMR signals can be enhanced in general, as stated by fact 3 in the statement on the slide, where it says that M0 increases with 1, higher sample concentration, 2, higher gamma, 3, higher B0, and 4, lower temperature. Note that the topic discussed in this slide is a separate issue from enhancing NMR signals due to spin-spin correlation using different experimental methods, which will be introduced later in the lectures. This slide is about NMR receptivity, which is a measure of how easy it is to acquire an NMR signal of a particular nuclear species. We want to learn the factors that affect the receptivity and how. First, let's have a look at a concept called absolute NMR sensitivity, A, which depends on the gyromagnetic ratio of the species, gamma, and the principal spin quantum number of the species, I, such that A is directly proportional to absolute value of cubed gamma times I times bracket I plus 1. There are two kinds of NMR receptivities: absolute receptivity and relative receptivity. The NMR absolute receptivity R depends also on the natural abundance, eta, in percentage, such that R is directly proportional to the absolute value of cubed gamma times I plus 1 times eta, and hence is directly proportional to A times eta. However, they only make sense to us if we compare them with a reference. People then introduce another concept called NMR relative receptivity, R S1 over S2, which gives us the ratio of an absolute receptivity of a species S1 to that of a reference species S2. For example, the relative receptivity of 1H over that of 13C, denoted here as R1H over 13C, is equal to the absolute NMR receptivity of 1H, the numerator, divided by that of 13C, the denominator. Since both 1H and 13C are spin half species, the I's and the I plus 1's are cancelled. The ratio is then simplified to the absolute value of cubed 1H gamma times 1H eta divided by the absolute value of cubed 13C gamma times 13C eta. So far, we have learned a number of concepts and formulae. Now, let's have a look at a spreadsheet table that contains some of the concepts. I'm going to do a bit of explanation about how the figures in the table are calculated. First, I want you to understand that in the table, only nuclear magnetic moments, spin quantum numbers, natural abundances, and field strengths are given. The rest of the figures are calculated with formulae using these figures and two famous fundamental physical constants, for which the values are given in row 5 and 6. For example, the gyromagnetic ratios in column F are calculated with G equals bracket EJ divided by IJ bracket times 10 to the power of 2. where EJ is calculated by DJ, and DJ is calculated by the nuclear magnetic moment, CJ. The NMR frequencies in column G, H, and I, on the other hand, are calculated by the fundamental equation of NMR with gammas and different field strengths. The absolute sensitivities in column K are calculated with gammas, I's, H, and mu n, which is a nuclear magneton. The relative receptivities in column M are calculated with absolute sensitivities and natural abundances. This table is uploaded onto Moodle for your reference, and it will be one of the tables used for the exam. You are expected to be familiar with the explanation of the formulae and the use of these formulae for the calculation of some figures. This is a summary for what we have learned in the last few slides. We learned that nuclear precession frequency is correlated to the transition of energy. And if the unit of the spin energy is chosen to be quantum energy unit H or H bar, then delta E is simply equal to the angular frequency. We learned that the net spin population N-net is directly proportional to N total, to gamma, to B naught, and inversely proportional to the temperature T. We learned that the macroscopic nuclear magnetic moment M naught is directly proportional to N total, to cubed gamma, to the square of B naught, and inversely proportional to T square. And finally, we learned that the relative NMR receptivity is the receptivity of the species over that of a reference species such as 13C.